The emergence of new physics has profoundly transformed humanity's understanding of astronomy. Modern cosmology was born, marking the transition from philosophical speculation to scientific research. New astronomical discoveries in the 1960s strongly supported the Big Bang theory. Astronomers observed extremely distant star-like objects called quasars. These are actually supermassive black holes consuming matter, existing only in the distant past, proving the universe evolves. The cosmic microwave background radiation permeates all space, matching Big Bang predictions. This evidence established the Big Bang theory, replacing Newton's static universe model. Hawking's research on black holes began from this foundation. Now, let's move to part 3 and discuss black holes. When a massive star exhausts its fuel, it explodes catastrophically. Without thermal support, the core collapses under gravity into a dense object. This is a black hole. To become a black hole, the Sun would need to collapse from 1.4 million km to 3 kilometers diameter. Compressing Earth to black hole size would reduce it to 2 centimeters. With gravity so strong, light can't escape. This dark, gravitational pit gives black holes their name. A naked black hole without surrounding matter would be invisible in dark space, but matter falling into black holes creates fascinating phenomena. The intense gravity accelerates matter to extreme energies, making it glow. Material emits intense radiation before crossing the event horizon, making feeding black holes the brightest cosmic objects. Cygnus X-1, discovered in 1965, was the first observed black hole candidate. The study of black holes like X-1 represents one of humanity's greatest intellectual leaps in cosmology. Based on Einstein's genius, imagination, and mathematical reasoning, Hawking and others deduced many properties of black holes without direct observation. In the 1960s, Hawking began studying the black hole singularity problem. A singularity occurs mathematically when dividing by zero creates infinite values. Hawking and Penrose proved through general relativity that black holes must contain regions of infinite density. This is all known physical laws break down at singularities. Human scientific knowledge becomes invalid at singularities, making them popular in science fiction. The 2014 film Interstellar depicted time travel through singularities. We still don't know how to enter black holes and survive. The film assumes alien-provided solutions. Second, the no-hair theorem. In 1971, Hawking proved rotating black holes must be axisymmetric, leading to the no-hair theorem. The hair metaphor means black holes have no complex features beyond mass, spin, and charge. Regardless of original matter or shape, black holes remain fundamentally simple. Black holes are remarkably simple objects. Third, the area theorem. Hawking discovered black hole area always increases when matter falls in. Merging black holes create new areas equal to or greater than the sum. This non-decreasing property is called the area theorem. When black holes merge, lost mass radiates as gravitational waves. These are gravitational wave events. In 2015, LIGO detected gravitational waves. This discovery won the 2017 Nobel Prize in Physics. Fourth, black holes aren't black. The area theorem resembles thermodynamics' entropy law. Entropy, a thermodynamic quantity, measures the degree of disorder in a system. What does the law of entropy increase? In thermodynamics, systems without external work done will always increase in disorder. Like children's rooms where toys and books never organize themselves. This demonstrates entropy increase. This analogy implies black holes would have temperature if possessing entropy. But how could light-trapping black holes emit radiation? Hawking resolved this paradox by applying quantum mechanics to black holes. This became known as Hawking radiation. Quantum mechanics reveals that vacuum isn't truly empty, but filled with virtual particle-antiparticle pairs. Quantum mechanics permits temporary energy borrowing from the vacuum. Energy cannot be created from nothing. These particle pairs consist of positive and negative energy partners, existing briefly before annihilating. Macroscopically, their total energy remains zero. Hawking proposed such particle pairs near black holes, event horizons, positive and negative energy pairs. Negative energy particles fall into the black hole, while positive energy ones escape. This creates the observable effect of black hole radiation. Thus, Hawking concluded, black holes aren't truly black. Interestingly, larger black holes have lower temperatures. Hawking radiation from stellar mass black holes is undetectably faint. Current observational capabilities cannot detect this radiation. Verifying Hawking radiation remains a long-term scientific challenge. In his final chapters, Hawking reflects on science-philosophy relations. Scientific progress has absorbed many philosophical questions. Cosmology was primarily philosophical before the 20th century. Post-Einstein, scientists can now rigorously study cosmic origins and evolution. Thus it became a scientific question. Though philosophers and scientists share common topics, their mutual language seems increasingly scarce. This ultimately created a divide between humanities and science. Hawking noted most scientists focus on developing cosmic theories but rarely ask why, while philosophers can't keep up with scientific advances. Hawking urged maintaining deep questioning alongside celebrating scientific discoveries. Why does the universe exist? This is humanity's shared fundamental question. Now, let's conclude our journey through a brief history of time. The book chronicles cosmic conception, evolution, and key black hole discoveries, humanity's changing cosmic views. From flat Earth to geocentrism, heliocentrism, infinite cosmos, to Big Bang theory, progress driven by physics. Aristotle and Newton established classical physics, explaining celestial motions through gravity. 20th century physics shattered limitations with two pillars. General relativity explains gravity as space-time curvature. Quantum mechanics reveals subatomic uncertainty. These breakthroughs birthed modern cosmology. Hawking's early cosmological research focused on 4 black hole breakthroughs, 1 singularities enabling theoretical time travel, 2 no-hair theorem defining black hole simplicity, 3 Area theorem ensuring merged black holes only grow. 4 black holes aren't black. Hawking radiation theory. Scientists continue probing black hole radiation as human curiosity drives cosmic exploration. We live in an era of accelerating cosmic discoveries. A brief history of time captivates by revealing cosmic mysteries operating beyond conventional understanding. This concludes our interpretation of A Brief History of Time. The audiobook notes are below the audio. See you tomorrow.